Very good evening. Yeah, we have to start with geomagnetism. Thank you. Thanks for that. So today's lesson plan, let me start straight ahead. And today you will find answers for several questions. Okay. Like from mountains, volcanoes to earthquakes. Like even though the entire topic is not possible to complete, but definitely volcanoes can be done and the foundation will be provided. So today's lesson plan, we need to start from geomagnetism. You might think that geomagnetism an odd off topic, not exactly. This will be very essential because through geomagnetism we'll explore paleomagnetism and then seaflow spreading, and these two will serve as the foundation for the important topic for today, and that is plate tectonics. Okay, once plate tectonics is over, we shall cover related topics of volcanoes and mountain building. Is it clear? So today you should be in a position to pinpoint, okay, where exactly the mountains are present, why volcanic activity is more specifically in certain parts of the world. Okay, just like climatic concepts, once the climatic regions were over, you were in a position to get a comprehensive idea, isn't it? So similar to that, once the plate tectonic section is over, your idea will become very clear. Now the point is, before we move to plate tectonics, actually, we need to understand how this plate tectonic theory came into genesis. So for that only, we are learning geomagnetism, and then these two evidences. These two evidences will prove fundamental. Thank you. Will prove fundamental for moving towards plate tectonics. Okay. So with that, let me start with the first definition for today: geomagnetism. Okay. So after continental drift theory. Thank you. So that's where we left off. So after that, this is the topic. Very good evening. So last session you would have seen that Alfred Wegener's continental drift theory was a failure. Like it was heavily criticized, not acceptable and all that. So today we'll see what theory was tried to overcome, and we'll start with this topic. See, possibly a very simple definition. Okay, geomagnetism is the magnetic field associated with the earth, magnetic field associated with the earth, and is a result of the structure of the earth's core. Structure of the earth's core. Full stop. Okay, so in the definition itself, you're trying to understand something which is very close by. Okay, what is the causative factor? Is it clear? So geomagnetism, no complications in the definition of the word actually. Geo means earth and magnetism is to represent the magnetic field associated with the earth. Now thing is, important point is the causative factor I've clearly given. It is to the structure of the earth's core. I did not even say earth's interior, but I've used the word core. Okay, so first we learn the mechanism, then something called as polar reversal, then what exactly is this paleomagnetic principle? Ready? See, to really understand and appreciate what exactly is this Earth's core structure, I'm going to take you to 7th and 8th standard physics. Now, this is for students from non-science background. No worries, I'm pretty sure, 100% sure you know what exactly this is. I think you remember electromagnet. Okay, how electromagnet is getting created. For example, you'll have this diagram in your school books. There'll be a metal piece. 7th and 8th standard, not even 11th and 12th, metal piece. This metal piece will be encircled by a coil of wire, right? And when you pass current, okay, which is usually represented by I, okay, this current will generate a magnetic field in this particular metal piece. It will magnetize it. Remember, so by passing a coil, current through a coil of wire around a metal piece, you will be in a position to create a magnetic field. Like this is the principle behind electromagnet, widely used every day in most of the appliances, though we may not realize it. See, actually, your Earth's magnetic field is a simple extension of this principle. You might be asking me how exactly it is. We'll try to recollect the structure of the Earth's interior, that is the core especially. Your Earth's core is slightly different and complex compared to your mantle and the crust. The inner core is solid medium, whereas the outer core is liquid medium. Remember, so if you draw the diagram for the Earth's core, you will actually find something very similar to an electromagnet. Let me draw that for you. Just keep this at the side. We'll see whether the Earth's core is matching this diagram. So this is the Earth, and not concerned about the crust and mantle. What we are concerned about is what is actually in the center. Okay, so let me draw the inner core. The inner core is solid. And you clearly know from the previous discussion that this solid core is primarily made of nickel and iron. Both are ferromagnetic materials, and you know iron. Iron is a very strong ferromagnetic material, which means it has a very strong affinity with magnetism. So this metal piece which you find, this metal piece which you find as part of the electromagnet is analogous to the metal piece which you find, not the metal piece, to the solid inner core. Okay, so this is the metal piece, this is the solid inner core. That's the analogy. Okay, now you might ask me, now how exactly do we create this current? Let me recollect something for you. The outer core is liquid medium. This is liquid, right? The outer core is liquid. Now, it is not just liquid. You're not talking about a stationary liquid. The point is, the earth is rotating. See, understand, if it's just a stationary liquid, then you're not going to create a current. But once the earth begins to rotate, and I'm talking about 1,000 kilometers velocity, very, very high velocity, your atmospheric system and your hydrosphere system, which on the outer surface of the earth is going to rotate. We have learned in detail about atmospheric circulation, your meridional circulation, jet stream, cyclones. So many circulation systems are outside the earth. Now, similar to that, at the inside of the earth, okay, when the earth begins to rotate, in the outer core, okay, in the outer core, which is a liquid medium, you will be in a position to generate movement, currents. And as you have guessed it properly, it is different in the northern part of the liquid core and southern part of the liquid core. The details, the technical details are not required because Coriolis force is going to be different in northern hemisphere and southern hemisphere. But the point is, the liquid core is not stationary, but it's moving, right? So look at this particular diagram. The electrons are moving. So automatically you'll ask a question, well, here only liquid core is moving. Like, where are the electrons to generate the electricity? Only when you have electricity around the metal piece, you will create magnetism. Yes or no? So you understand? I've already told you the clue in the previous session. You just need to make the connection. When we discussed presence of radioactive materials in the previous session, you do remember that the core has immense amount of radioactive materials, radioactive elements, especially uranium. Right? We discussed these radioactive elements to actually provide you with the understanding that a good percentage of materials is present close to the asthenosphere, or it's actually there in the asthenosphere. See, radioactivity is a phenomenon. Try recollecting from the previous session. Radioactivity is a phenomenon where any element tries to radiate energy. So once an element tries to radiate energy, the atomic structure gets disturbed. That is why you create a ductile medium in the asthenosphere, remember? So in this region, your outer liquid core, due to the presence of radioactive elements, you create a large number of ions. The process of ionization goes on. So there you have your charged particles. Very simple. The metal piece connotes to your inner solid core. The current which is passing around the metal piece is analogous to the ions which are present in the outer liquid core. So metal piece and charged particles moving around creates a current that results in the Earth's magnetic field, as simple as electromagnet. Very simple. That's all. Is it clear? So take this down. Okay. Earth's magnetic field. The charged particles of the outer liquid core revolve around the solid inner core, creating the magnetic field, or creating Earth's magnetism, or creating geomagnetic field. Any statement would be fine. Okay, so you clearly see it's a very fundamental principle. Thing is, we won't realize it. Okay, the phenomenon might seem extremely complex only when you delve into different parameters of how much composition of radioactive materials is there, or what is the variation between the northern hemisphere, southern hemisphere. But that detail is reserved for technical subjects. If you're learning this as a subject matter in your degree, then you can delve into the details. You're just trying to crack an exam, and this foundation is more than enough. The basic idea. Is it clear? So once you have taken this down and understood, use the word finished. I'll proceed further. Okay. Next, we're going to look at representation and movement. Use the word finished. I'll proceed. Two responses, one more, I'll proceed. Yes, thank you. Now we need to understand, like, how do we actually represent this, like on a scale? Like if you're trying to do some mathematics and you want to try to represent this, how exactly it is done? Well, our traditional representation is by using a bar magnet. So this is how we do it. So if this is going to be my Earth, okay, this is my North Pole, geographic North Pole, 90-degree north. And this is my geographic South Pole, 90-degree south. Okay. The Earth's magnetic field is usually represented like a bar magnet. And understand this. There is no magnet in the center. For our representation, for our own calculation, we represent something like this. So if this is my Earth's axis, this bar magnet is tilted at an angle. Let me explain. Hold on. Okay. Pay attention. This bar magnet can be in any position. I'll explain how. Hold on a second. So right now I've taken a tilted position. You get the idea? So with reference to the Earth's axis, the magnet is tilted at an angle. We'll call it theta. Some angle, theta. Okay. With reference to where the North Pole's attraction is very, very strong, we call it as magnetic north. And where South Pole's attraction is very strong, we call it as magnetic south. Okay. So it is not necessary that your geographic north doesn't change at all. It is simply a North Pole. Geographic south is simply a South Pole. Okay. The point is, this bar magnet is not going to be constant. I mean, the representation is not constant. It's constantly moving. Is it clear? That is why theta, I'm not defining any value because it changes over a period of time. Theta is called as a declination angle. Declination angle. So it is the angle between the represented bar magnet and the Earth's axis. Okay. Now to answer the question, like why exactly is it tilted? Why can't it be straight? Well, the answer is no one knows. I'm not joking. I'm being serious. No one really knows what is actually happening. See, that's why you use this word theta. Theta is not constant. What I'm trying to say is this theta can be negative. I mean, your bar magnet can be here. You get the idea? Your bar magnet can be straight also, or it can even be inclined. Any possibilities there, it can move around like this. And please don't worry, it is not going to happen in your lifetime. Okay, this type of movement takes thousands and thousands of years. Okay, so why exactly it is moving? It is still under research. We don't know the answer. That's the simplest one I can give you, but I can definitely show you the pace of movement. For that, I will use a picture. Once you have taken this, theta is not constant. That's something you need to remember. The theta is not constant. It can change. Reason still unknown. Okay, but the change takes thousands and thousands of years. It's not something which will happen in your lifetime. Okay, so for that we will use a picture. Is this responsible for creating auroras? Yes, we will discuss auroras. Hold on. Just wait for 1 or 2 slides. Use the word finished if you're ready. We'll just see one simple picture. Not a picture actually, it's a representation. It's an image. It is a little bit confusing. There is nothing to get confused here. Your confusion should only come if you ask this question, why? Okay, if you're asking this question, why it is tilted, I've already told you the answer. I don't have any answer. There is no answer. You can search any website, no problem. We just know for sure. See, let me tell you this. The magnet can be like this, exactly matching 90-degree North Pole and South Pole. The magnet can be west of it. The magnet can be right of this. It can move anywhere. It doesn't matter. Why is it shifting? It doesn't know. I'll show you a picture. Hold on a second. Patience. So why question, if you ask me, I don't know. It's still under research. See, the problem with the Earth's interior is we really cannot go there and explore. All we can know is only observe things. Let me just show you how the magnetic North Pole is shifting. Yeah, I think this is very good. Good. Now pay attention to this image. Look at this one. This is my North Pole, 90° north. This is not going to change it. That's the point. This is your latitude, 90° north. Whereas this one is actually your, like based on values. Because look at the year right now, 1900. Like based on our own calculations, like based on where the magnetic attraction is maximum for your magnetic compass, you know that this is where my strongest magnetic attraction is. So 1900, you might be thinking you do not know the place. Actually know the place. You know where exactly it is? Try to recollect map reading. This is in Queen Elizabeth Islands. Remember Queen Elizabeth Islands? Queen Elizabeth. You'll cross over from Greenland, then you'll ask for help from Baffled. This is Baffin Island. You're getting the location. This is Baffin Island. This is Queen Elizabeth Islands. So 1900, you're very close to Queen Elizabeth Islands. That is in the northern portion of Canada. 1940, 1980. So it has taken close to 80 years for a migration of 100 kilometers, possibly 100 or 150. So it's moving north. Okay, 1980. 2000, it's actually moving further north of Canada. It has exited the Queen Elizabeth Islands, is moving towards North Pole. Position in 2010 and 2020. You know where it is supposed to go? It is believed that this geographic North Pole, you know what is happening is, listen carefully, from somewhere in Canada, it is moving closer and closer and closer to North Pole. Oh, yeah, sorry. It's moving closer to North Pole. That's what I told you. Theta is not constant. Theta shifts every 10 or 20 years. Meaning makes sense. So after a point of time, it is believed, based on the picture, this can actually take you, if you listen carefully, you move further, possibly you can enter Siberia. So maybe the maximum magnetic attraction, you'll find it over Siberia. I think now with this picture, you get it clear. Like this is something which we measure. This is what is happening. Okay, this is something which we observe. It is not hypothetical. Okay, please note that. Okay. Confusion regarding axis inclination of revolution and magnetic poles in geographic north and south axis. See, please note, when you say this word Earth 2 is tilted, I'm not talking about Earth's axial tilt. That's why I try to make it simpler for you. Okay, I'm not talking about Earth's axial tilt of 23.5. I'm talking about Earth's axis itself. You get the idea? Because if you take that into consideration, it becomes only more complex. I can draw the diagram. It will confuse others. If you've already understood the concept, don't look at this diagram. I'm drawing it for you. You understand? I never spoke about the Earth's axis. You asked for it. So don't blame me for drawing this diagram. Please understand. I'm not talking about this one. Okay, like we had taught this, no? Earth's axis is 23.5 degrees with reference to the vertical. Okay, I'm not talking about this. I'm talking with reference to Earth's axis, with reference to this. This is what I call theta. Meaning makes sense. This is vertical. This is not the Earth's axis. If you understood the previous diagram, forget this. I just had to do this since you asked me the question. This is not constant. Theta can move like this anyway. That's what I told you. I'm talking with reference to Earth axis, not vertical. Did I answer your question? Let me know. Okay, fine. Good. Thanks for the response. Thank you. So just to make clarity, in case if anyone still had confusion, this is what we are talking about. Now, we have seen the image, something which we have registered. So theta is not constant. It keeps changing. Now, let me drop something very important to you. See, hold on a second. Theta dancing like this is not a problem. You know why? See, at the end of the day, the magnetic North Pole or magnetic South Pole is somewhere closer here. So even if it is going to move in this direction, even if it is going to move in this direction, your magnetic compass is, if you're operating from Chennai, operating from United States of America, you won't be experiencing big deflection. At the end of the day, it should show one particular direction. You can definitely know your west, east, and south. You're flying an aircraft, you want to know where it's not, just get a rough idea, it'll be more than enough. See, actually, there will be chances where theta, not just theta is not constant. In some instances, your entire magnetic field can actually flip. You know what I mean? Actually meaning it is possible, it is very much possible that your magnetic field can become something like this. This is what we mean. Okay. Complete reversal. Now, some of you might be thinking I'm joking. No, I'm not joking. We have recorded evidences. Of the Earth's 4.6 billion history, we have at least 50 to 60 events of complete magnetic reversal. Now, this magnetic reversal takes place on an average over a period of 700 or 350 or 700,000 years. It's a very long period of time. Okay, so this is also possible. So you can write the statement, apart from migration, the magnetic field can completely switch between poles. Completely switch between poles, and we have evidences. I want to elaborate more on this point. Please be patient. Okay. Just hold on. I need to add a few more statements. I'll read the statement again and then explain. Apart from migration, the magnetic field can completely switch between poles. The point which I want to add is this switch doesn't happen in a single day. I've told you it takes place over hundreds and thousands of years. At the same time, it takes place very sequentially. For example, if the strength, let's assign some percentage. Let's say the strength of the magnetic field is quite severe. Maybe it's 100% strength. Once the flipping process begins, let's say it's going to flip over. Okay, it's very slow. From 100%, the strength of the magnetic field will decline 90%, 80%, 70%, so on and so forth. So when it declines, consistently declines after a point of time, let's say it comes around to 60% or 55 or 50%, during that time period, the entire magnetic core collapses. You get something like this. This is the transitional phase as far as we have observed. You'll get multiple poles in this sense. Magnetic north, magnetic south, magnetic north, magnetic south. Something like this. Complete structure is actually collapsing. After collapsing, to reinforce a reversal magnetic field, it won't be at full strength at the start. It reinforces, it flips over, again starting from 60%, 70%, keeps moving up until 100%. So this is the process. The entire process takes 350,000 to 700,000 years. It's a very lengthy process. And it's been some time that the magnetic reversal has happened, but as far as we know, is that reversal has been documented. Okay, and the documentation has been in rocks. Through geology, we will understand how exactly it is. Now, point to be noted, you asked a question on auroras, isn't it? I will deal with auroras, but possibly later at the end of the session, after we finish plate tectonics and the discussion on volcanoes and mountain building, because this discussion will directly lead us to paleomagnetism. I just don't want to diverge from that. Okay, I think you got the idea. This is a very slow process. We have documented collapsing of the magnetic field where you don't have clarity or where exactly is your magnetic north pole and south pole. Now, you might be thinking this has no relation with the evolution of the Earth. Well, let me tell you. The next topic will throw much light on it. The topic is this: paleomagnetism. Paleomagnetism. Paleo means old. Magnetism itself is the study of magnetic properties. Study of magnetic properties of old rock structures. Very, very old principle. Okay. Paleo means old. Magnetism is the phenomenon of magnetism itself. So it's the study of magnetic properties of old rock structures. Now, before we go to this, I want to establish two concepts firmly, just like we did for Coriolis force. Okay, because these two concepts, pay attention. Concept 1, concept 2, when we try to integrate again, similar to Coriolis force, I'm not going to write any definitions on the board. I just have to take it up that you're following. So do respond in chat box when I ask these questions. So we're going slightly for examples and outside discussions. Then we'll come to the concept of seafloor spreading. Ready? Hope you're ready. I'll just start with this. Concept 1, 2, and then using the same thing. Hope you're ready for C1. A very large bar magnet, North Pole. Okay. I'm taking a metal piece, a strong ferromagnetic substance, iron, I just place it here. Okay, let's say the metal piece stands in this direction. It stands like this. Okay, sorry, metal piece is not visible for you. Metal piece stands like this. This is the orientation, something. This is its position. Got it? Now, another bar magnet, but this time, or the same bar magnet, every bar magnet has a both North Pole and South Pole. There is a South Pole right now. Okay. Now, listen carefully. I am not changing the metal piece. I'll take the same ferromagnetic substance. I place this metal piece near the South Pole. My question is simple. When I place this metal piece in South Pole, will it remain in the same position or will it change? I'm talking about the position of the metal piece. Will it stay like this, or I place it here, will it change? Give me an answer. Same or change? Thank you. Correct response. It will change. See, the reason being North Pole and South Pole actually have differences in terms of magnetic lines of force. Magnetic lines of force leave North Pole, and in South Pole, magnetic lines of force enter actually. Just like charges, like poles will repel each other, unlike poles will attract each other. Meaning makes sense. So same metal piece, if you're going to place it near South Pole, when there is a reorientation, they'll flip in the opposite direction. You can't have the same position, not possible for the same metal piece. Meaning makes sense. So it will change. Change is the right answer. Got it? Why? Because like poles like poles repel and unlike poles attract. Let's come to the next concept, C2. Our bottle, used for demonstrating everything, right? Take this bottle. Now, let's say that I ask this in class and they gave one weird answer, first of all. Like, if you want to make this bottle, what exactly will you do? That was a question I asked, and the students actually came with the answer. First, they will mine copper. Very good. After mining copper, let's say you purify copper, and I say that I want this particular water bottle. This is what you'll be doing. For example, if you want the shape of the bottle, you can get a casting for this particular diameter, size, and all that. You get a particular cast. After casting, what you'll do is you'll take pure copper, which you've extracted, or you can, of course, you need to add some impurities for better ductility. After adding some impurities, you will melt it, right? Because that's much easier. You make it to molten state. In molten state, this particular casting which you have, you'll try to pour it inside the casting. Once you pour it inside the casting, that particular shape will be obtained, whichever shape I asked you for. Right? So that's how metals are actually modified into different shapes. Pay attention. Simple question. Copper is in molten state. Okay, copper is actually finally reached the shape. It is cooled down, final shape is reached. Now, if you want to change again, let's say that I ask you, I don't like the bottle. I want something like a copper cup or copper jug. Okay. 1, 2. Which is easier to modify again? Would you like to again start from the molten state, or is it much easier to create this jug through molten state, or this one? Which is more easier for you to modify? Yeah, it is actually in the molten state again. See, the reason being, here, if you want to take this again, you need to take this copper, then you need to bang that copper, stretch it out and all that. You need to change the ductility pattern. You need to again modify the structure. Makes it much, much difficult. You already have molten copper. Just find a casting, that's all. You find the reference casting, then pour it to that particular structure. You will get this particular bowl. There is no problem at all. See, point to be understood is, it's easier for manipulation, much easier for manipulation whenever things are in molten state. You've already reached the final state, the cooling process is over, and the shape is cemented. Changing this is extremely difficult. You need to use your tools, break it, stretch it apart, and then reframe the entire thing. Rather, you already have the reserve, just get the casting, it's done. Meaning makes sense. So manipulation is much easier in molten state. Very difficult if I've reached my final state and then solidification process is over. You can't do anything. Okay, so that's the point I wanted to convey. C2. And now we are going to use both C1 and C2 together. Hope you're ready. The thing is, the big magnet which you saw is actually a reference for the Earth's magnetic field, this one. Okay, Earth's magnetic field. And the second one which you saw right here, okay, is with reference to ferromagnetic materials. Listen carefully. Ferromagnetic materials which come and reach the Earth's surface during volcanic eruptions. See what happens. At a point of time, this is my magnetic field. Okay. There is a volcano here. From this volcano, there is an eruption from the asthenosphere. From the volcano, all types of substances are actually going to come out. Definitely iron will be there. Iron is one of the abundant elements. Okay, fine. Not very abundant, but still. Let's say there is a ferromagnetic substance which is in molten state. Pay attention. In its molten state, from its molten state, it is going to slowly solidify into a rock structure. Yes or no? The small amount of iron mineral which you find right now will actually be part of a larger igneous rock. Okay. So what you're doing is, from the molten state, you're slowly solidifying. See, understand, this ferromagnetic material is going to orient itself, or it's going to position or orient itself based on the magnetic field of that day. That particular day, whatever be the magnetic field, based on that, when the ferromagnetic material is getting solidified, it will align in one particular direction. The point is, once it has aligned, it is that particular orientation or position is not going to change, because you've already reached the solidification state, similar to that water bottle. Meaning makes sense. I will call that alignment of this ferromagnetic mineral after solidification as P1 for reference. Like, it is aligned in particular position 1. Let's say 250,000 years pass. It can be anything. I mean, your magnetic north and magnetic south can tilt in any angle. I will take an extreme case to make it much easier for you to understand. Let's say the magnetic pole completely flips. Okay. So magnetic south is there, magnetic north is there. Volcanic eruption. From this volcanic eruption, one more iron ore comes out. An iron mineral comes out, a good concentration of iron ore. Okay. Now this iron ore is again going to align in one particular position. Let me call it P2. Pay attention. My question is simple. Will P1 and P2 be same, or will P1 and P2 be different? Please don't answer wrongly. I will kill you. 3 answers are correct. Very good. Okay. It will be different. Just like we placed a ferromagnetic material between a north pole and a south pole, the position completely flipped, right? So similar to that, if the Earth's magnetic field is going to change, okay, from magnetic north-south is flipping to south and north, you cannot expect the ferromagnetic material to have the same orientation or position. It is going to flip. Okay. See, your ferromagnetic materials are like a digital record. Like when they are born, okay, there is a temperature called Curie temperature. They have the capacity to register what is the magnetic field of that particular day. You get the idea? That is why we use the study of paleomagnetism, studying magnetic properties of old rocks. So if you know the age of the rock, and at the same time, if you know the magnetic orientation of the rock, you'll be in a position to understand what could have been the magnetic field of that particular day, 250,000 years earlier, 1.5 million years earlier, maybe even 1 billion years earlier. That is how the paleomagnetic studies actually go. And that is the reason the studies were very important in actually providing an important evidence for the evolution of plate tectonic theory. And that is why we spend some time. This explanation is not there clearly in your NCRT. It just ends in few passages, basically. But you need to understand this particular concept, that a ferromagnetic mineral acts as a digital record. It can register the magnetic property of that particular day or that particular year, whenever it was born as a rock from a volcanic eruption. Let me talk about an observation, because always we frame our theory based on observation. And this observation is in Atlantic Ocean. See, if you look at your 20th century, especially the early part of 20th century, the two anomalies were both world wars, World War I and World War II. And of course, one economic anomaly was your Great Depression. Apart from that, there was very good amount of investment in scientific community, primarily for exploitation of minerals. Okay, and after your World War II is over, there is very good development of technology, because whenever you develop something in defense, you naturally implement the technology in science. So what happened is, they started scanning the Atlantic Ocean for minerals. See, my objective is not to help geography, because it's a boring subject after all. So companies will invest money to exploit what level of minerals are there. That is why they study magnetic properties. Maybe this particular mineral is more concentrated here, we can try to extract more. Economic exploitation. And in the Atlantic Ocean, they come up with an interesting observation. I will put you the observation, and from the observation, we will generate the theory. So what do they observe? So this observation is in the Atlantic. So in the Atlantic Ocean, paleomagnetic studies gave an interesting observation. Full stop. So what exactly it is? I'll show the observation, then we'll write theory. Okay, there was a volcano. Is it clear? Quite extensive. On either side of the volcano, yes, there were different types of rocks with different magnetic properties. But there was one catch. Look at this. So we will call this position 1 just for reference, P1. I'll call this P2. Finally, I'll call this again, P3. See, in the actual diagram, you will find names of different geologists, names of different geographers given to different each and every kilometers. You get the idea? This will be few kilometers, few tens of kilometers in width, few tens of kilometers. That is how it is. Okay. The observation is quite interesting because it's that with reference to the central volcano, you actually have alternating strips of land with similar magnetic properties on either side. Like these two are similar, you move even far away, these two are similar. You get the idea? So the observation is alternating strips with similar magnetic properties on either side of a volcano. This is my observation. I still haven't told you the theory yet. Position only changed, but material is same. Yes, of course. It's the material. It's the position which we are concerned about. At the end of the day, we're talking about ferromagnetic materials. Okay. It's only about how it orients. See, it's like when you're going to freeze, like Tom and Jerry, or you're going to stand like this or stand like this. That's all. That's the way it is. Okay, use the word finish if you're done. I'll go to the next slide and then try to speculate. See, we are going to speculate a theory, just like we did for the interior. Okay, I'll speculate something. Because it is through speculation that you can arrive at a particular theory. Okay, 2 responses. See, once plate tectonics is done, like, you'll get a comprehensive idea. You're moving towards it. Pretty sure before 6:15, I'll give you the idea at least of what exactly is plate tectonics, even if the theory is not complete. Fine then. So 3 responses. I'll proceed further. Now let's say I'm trying to speculate as such, then I'll arrive at the final theory. Listen carefully. See, if this is a volcano and this is my observation. Example. Writing the theory is pretty easy. Very simply, very, very simple to explain this particular theory. You know how? Through newspaper, Hindu newspaper, important for Union Public Service Commission exam, civil services examination. Look at this. Terida. 2 flaps of land. You get the idea? So if I need to explain this, it's very simple. What I say is that actually there is a volcano. Okay. The volcano started erupting. Once the volcano started erupting, material will deposit on either side. People, this is my hand. This is my hand. I take blade. I won't do that, I'm saying. I take blade and put one straight line. Blood will come only on left side and hit my face. No. Blood will come on left side, then it will flow towards this side. Blood will come to the right side also. Don't try this at home. See, once you put the gut to both left side and right side, equal amount of spilling is going to be there. So thing is, to explain this is very simple. So when volcano was there, volcano erupted. Once 50% of all that magma, lava material deposited on one side, 50% material deposited one side. Whatever was the magnetic orientation of that particular day, maybe it was 3.5 billion years ago, that is captured as position 1 in both cases, sir. Explanation over. Single volcanic eruption, lava settling on both sides. Once lava settles on both sides, then it is done. So very simple to explain this observation. But problem is, observation itself is complex. I don't have one. I have triple. Actually, if you look at the actual number of strips, it's more than 4. Okay, like for simpler understanding, we're looking at 3. Now, how do you explain this? Yes, speculation again. See what happens. Sir, there is a volcano first. Volcanoes there. This volcano is erupting. Okay. Once this volcano erupts, material will deposit on either side. So material is depositing. These ferromagnetic materials are trying to record whatever is the magnetic field property of the day. It is getting recorded, it's settled. So what did we have as P3 pattern? Just a second. Okay, just want to confirm. This is my pattern. Right, this is my pattern. The thing is, the eruption does not stop here. Let's take possibly 550 years, or if you want 800 years, maybe 1200 years, maybe 1500 years, any time. So over a period of 1500 years, the volcano is not erupting, but after a point of time, the volcano continues to erupt. So there is a second eruption. Okay, from the same central volcano. Now, whenever a second eruption happens, pay attention. See, this is going to be land on either side. Like this is P3. Okay, I'm just taking this. Next to volcanic eruption. When the next volcanic eruption happens, actually, the land will need to rupture open. Without the land moving away into either side, volcano cannot jump from beneath. You get the idea? Material is here. Okay, you think the spill will come automatically up? No, you need to open this area, then this eruption will jump and come to the side. See, I'm not saying that. The lava which is going to erupt is not going to settle on P1. It's not going to settle on P3 as the naming is in this case. Yes, some lava which will erupt will definitely try to come and occupy this certain area. But the point is, you look at these edges right here, the areas where I'm pressing the thumb, this one, the exact edge. In these particular edges, you're not going to have any disturbance at all. I'm talking about the last external stretch. Meaning makes sense. That stretch will escape. So when there is a volcanic eruption, as P3 moves away, new lava comes out. After 1200 years, definitely the theta angle would have changed. Once the theta angle changes even slightly, the position will not be same. So listen what happens. There is a volcanic eruption after 1200 years. So this land moves away, creating space. Okay, that results in new lava deposition, which is on either side. Okay, so this moves away. Got it? P3 right here. New material is getting created. This is P2. Meaning makes sense. So P3 moved away. Now, how do you explain the last one? I think you can do it yourself. After possibly 4,500 years, there is one more volcanic eruption. And when there is one more volcanic eruption, what will happen is land will move out even further. So once land continues to move even further, the final volcanic eruption, land will need to spread out again. So eventually, you will create a pattern which is something like this. You got it? So the trick is, this particular observation which we saw here, this one is possible only when land actually moves You get the idea? With reference to one more volcanic eruption which spreads out lava. You might be thinking, why break our head for all this? People, if not for paleomagnetic studies, if you had looked at this landmass, you would not even understand that there are alternating strips of different pieces of land, that their ages were completely different. Only through paleomagnetic studies, we for sure know that this is similar to this. P2 is same on either side, and P3 is same on either side also. Alfred Wegener, who actually proposed the idea in 1912, was right. Only thing is, he did not have proper evidences to support it. Now, with paleomagnetic studies, this is what we call as sea floor spreading. And immediately, every batch they come and ask us that, sir, you call it as sea floor spreading. Then how do you say land is moving? People understand. I'm talking about the land which is beneath the water moving. At the end of the day, it is land moving. Meaning makes sense. So now we have proper evidence that land is not constant, but land is actually moving. And this is firmly established only through paleomagnetic studies. If not for paleomagnetic studies, it is not possible at all. So also in P3, the rocks will be older than P1. Exactly. Very good. So if you look at the age of these rocks, the age of the rocks will be much, much older. These rocks will be very, very younger. Got it? So take this, use the word finished. Then I'll teach you plate tectonics. Like based on this, how did I come up with the idea of plate tectonics? Okay. If the overflow of magma in P3 over P2 is, that's what I told you clearly. I've addressed that question. Please don't ask me again. Last time I'm answering this. You look at the last volcanic eruption. See, it is not possible that P1 will be restricted here. Some amount of lava will spread through here also. Of course, this property will get changed. Get the idea? What we are concerned about is that the old property will get preserved because it is moving away. At least some kilometers of land or some meters of land will get preserved. That is more important. The spillover is unavoidable. Okay, so we don't have a scale right there. The spillover should only be at this particular meter. I think I've already addressed the question. Pay attention. Okay. Use the word finish if you're ready. One response, two more, I'll proceed further. Why would volcano erupt at the same time? Rishi, again, we don't know the answer for why your volcanic activity is concentrated only in specific regions of the world. For example, like I told you, it's Atlantic Ocean, right? So in Atlantic Ocean, we have something called as a divergent margin where there is concentration of volcanic activity. So the reason is not clear. Like we don't know the answer for that. Okay, see, if we know that, then if we know that, we'll be in a better position to predict volcanic activity in earthquakes. That's why our earthquake prediction is very poor. See, we can say a certain zone is hazardous, but we can never say for sure when the earthquake will come, right? Or something like that. Okay. So based on the above evidence, the final theory, see, which still stands today. Okay. This theory came up only in early 1960s. It's actually a very recent theory in terms of times. And point to be noted is, if we come up with a better theory in future, maybe it will replace this. I don't know. I'm teaching what is on the table right now. The plate tectonic theory. Let me write at least 2 pages, then I will explain. Hold on. Okay, this, why the again? This is a comprehensive theory. Comprehensive theory which explains the trinity of disasters. Trinity of disasters. Okay, we are talking about volcanoes, earthquakes, and tsunamis. It also explains mountain formation. Okay, just the introduction. Wait for 2 to 3 slides to get the idea. I haven't explained the theory at all. Patience. The orientation of the magnetic field of the Earth is known by examining the strips. Exactly. True. Yes. You match it with the age of the rocks, you will know at this particular time, okay, what was the magnetic field. Just a statement, that's all. Like, I really haven't written anything regarding the theory. I just said it's a comprehensive theory which explains the trinity of disasters, that is volcanoes, earthquakes, and tsunamis. It also explains mountain formation. Okay, Himalayan mountain formation properly explained through this theory. We will see how. Okay, I'll read it one more time before I flew. Comprehensive theory explains trinity of disasters, volcanoes, earthquakes, and tsunamis. It also explains formation of mountains. So what does the theory exactly state? Okay, it considers the earth to be made of lithospheric plates. Lithospheric plates, full stop. Sorry, the earth's crust. Important word was missed. Earth's crust to be made of lithospheric plates. The plates move or float over the asthenosphere, due to radioactive heat. Radioactive heat leading to convergence and divergence. I will explain the paragraph. Be patient. We will go to the world map also after this paragraph and you will get answers. Just hold on. I've just written the statement. I really haven't explained. Take it down. The plate tectonic theory considers the earth, an important part is earth's crust, considers the earth's crust to be made of lithospheric plates. The plates move or float over the asthenosphere. I think you remember asthenosphere, the upper portion of the mantle, solid ductile medium. Due to radioactive heat, I believe you remember this also. Where does radioactive heat come from? Because of presence of uranium, leading to convergence and divergence. Convergence to meet, diverge, move apart. I hope you're ready for this. See, this is just the basic introduction. I'll repeat the same thing in volcanoes. Repeat the same thing in mountains. By the time you repeat it in earthquakes, you yourself will write the theory. It's as simple as that. Just the basic idea I'm providing. The thing is, let's say this is the crust. Now, first of all, the one you should understand. I'll say one statement. Say whether you have doubt or not. Statement is this. Thermocol floats on water. I'll repeat again. Thermocol floats on water. Any doubt? Thermocol floats on water. Very good. Because large scale experiments were done in Tamil Nadu. So you should definitely know that. Okay. People listen. Thermocol floats on water. If you have doubt, put thermocol over water and see. Okay, I'm not going to explain beyond that. Now, what I want to conceive is visualize a water globe or water ball. Globe or water ball, imagine. Surface completely made of water. So what you do is you take that water ball, take thermocol, cut different pieces of thermocol and then float. For example, North America thermocol, South America thermocol, Africa thermocol, Antarctica thermocol, all these thermocol you just place over water. Thermocol will start floating over water, different continents, ball. That is plate tectonic theory, that's all. Plate tectonic theory considers the Earth's crust to be made of plates, and these plates float similarly how thermocol technically floats on water. In this case, the piece of thermocol is reference to different parts of Earth crust, and the water which we are talking about is your asthenosphere. So if these are different plates, okay, when these pieces of thermocol float over water, they can either collide against each other or they can actually move apart. Now, where does this energy come from? For that only we use this word. It comes from the radioactive heat of the asthenosphere. And this will explain the trinity of disasters. How? Pay attention. Let's say that this is one plate actually, one single plate, one portion of the crust, single plate. My head is inside the, pay attention properly, my head is inside asthenosphere. Correct? If I'm in the astrosphere, I have large scale access to radioactive heat. So see what I'm doing. I'm going to heat the plate. Shall I? Heating this particular area. So once I start heating consistently, this area will slowly start melting. I heat again. The heat will try to break open this area and come out. See? Once you start heating and the ground begins to shake, this shaking is nothing but your earthquakes. You got the idea? Let's say the heating continues. I split the earth open. You slowly get your volcanic eruptions coming in. This is your volcanic eruption. Meaning makes sense. Now these volcanic eruptions, once they reach the Earth's crust, you clearly know what happens, right? They will form rocks, formation of igneous rocks. If it's going to be underwater, the cooling will be very, very rapid, creating basalt. If it is over land, okay, like if it's an intrusive igneous rock, it is going to create granite. But mostly it is going to be basalt, at least in this particular case, because it's reaching the Earth's surface. I break open volcanic eruption, rock formation, volcanic eruption, rock formation, volcanic eruption, rock formation. Once the rock is completely formed, this is my mountain. You get the idea? The land is actually completely formed. You got it? So this is divergence which we are talking about. Divergence is moving apart. So due to radioactive heat, you had your earthquakes, volcanic eruptions, and then my mountains. Mountains are formed after igneous rocks. Got the idea? That is with reference to divergence. Now pay attention again. See, if there are two plates and the two plates are moving away, okay, there'll be one more plate here. Get the idea? So if I move here, he'll go and hit it. Yes or no? Plate, it's not that only one plate is there or two plates is there. Several plates are there in different parts of the earth. Once you push this, he'll go and hit this person. So let's talk about convergence, collision. Somewhere divergence is happening. Both of them go hand in hand. We'll see the world map also. So once you have divergence from one area and it's going to push up in one direction, there will be naturally collision. Two people are standing. I push one person, first person will go and collide with second person, right? See what happens. Once there is convergence, when two people collide, one individual will be stronger than the other individual. It's very natural. No two players will have the equal amount of strength. Impossible. Because the size is different, the composition is different. See again, convergence. Let's say one person is heavy. Whichever person is heavier and denser, he'll have a natural tendency to lay down. He will begin to sink into astrosphere. Got the idea? Whichever person is weak, he will tend to float. He's not going to sink down. Let's say two plates are there, and these two plates are going to collide. The person is dense, he's heavy, this person is lighter. So whichever person is lighter, he's going to face more crunching and crushing because he's weak. So when two plates collide, he will get deformed. See what happens? Deformation, collision, mountains. You got the idea? This is technically a mountain. The entire book is folding apart. So whichever plate is lighter, he'll experience immense amount of collision and he'll become mountains. Got it? Now see what happens. If this person is lighter, he becomes mountains. The denser person is going deep in. He's going deep in. He's going into the astrosphere. Who's there in the astrosphere? I am there. Radioactive heat. See what happens? Collision. Mountain on top. This you see over land. He's coming inside now. I will heat him. Once you start heating, he will begin to melt. Once he melts, the plate will shake. That is the earthquake again. Because naturally two plates are colliding. That will lead to more and more energy loss. And that will lead to more and more melting from the astrosphere. That will lead to more and more earthquakes. Meaning makes sense. Now at the same time, once pressure buildup goes on, breaking this particular mountain, you'll have volcanic eruptions also. Okay, because there is so much of fractures, and through these fractures, all the built up pressure will actually explode as volcanoes. Got the idea? Just with a simple theory of divergence and convergence, you can pretty much explain volcanic activity, mountains and earthquakes in most parts of the world, even though there'll be certain anomalies, which we will also explore. You got the idea? This is a foundation for plate tectonics. We'll go to the world map and we'll try to be more specific right now. What I gave you is just the general idea. Okay, so now let me be very specific. Got it? Now before we go to the world map, I think this is established, right? Okay. The plates are classified. Plates are classified based on size. There are 7 major plates. 7 major plates are there. This you should definitely know. All the 7. Okay, they are. I'll just give you the list right here. North America, South America, Africa, Eurasia, Indo-Australia, Antarctica, and Pacific. Pacific is the largest one. Very big plate. Pacific. Okay. The 7 major plates. See again, Wikipedia, if you go to Wikipedia or any other general website, they will tell you regarding square kilometers. Okay. Major plate should have at least this particular area of square kilometers. Please note that is way too subjective, because we have something called, as I will write the others, micro plate is there, you have minor plates also. So that value is subjective. Just understand major plates at continental scale. You can clearly see North American continent. We're talking about large continents. Minor plates, lesser surface area. Micro plates, even smaller. Just know that it's decrease in size. If you know that, that's enough. The mathematical numbers is not consistent. Different websites give you different values, so numbers you need not rely. The general idea that one is large and the others are small would do. Okay. You also have minor plates, and then this is 1. Yeah. Under major plates you have 7, minor plates, and then micro plates. See, I'm not giving the list of minor plates and micro plates because the numbers are too numerous. See, the NCERT says 22 minor plates, but please note there is constant updation. So it's actually more than 22. Micro plates will get close to 65, 70. Okay, that much is not required. Which is required is which are the important countries. We will see relevant examples also. At that time, if you know the basic idea, that will be enough. Wait for 2 more slides. I will show the world map. What is Pacific plate? Pacific plate is a major plate. That's all, man. That's all. Pacific plate is a major plate. Pacific Ocean, it's technically a plate. Shall I proceed further? Okay, you need at least 1 more slide. There is 1 more classification. Then I will show the world map. Please be patient. 1 more response, I'll proceed further. Right, thank you. So first is classification based on size. You can also classify them based on composition. Based on composition. As continental plate. Continental plate. This is made of granite. Okay. This is thicker but lighter. Thicker but lighter. Or it can be ocean plate, oceanic plate. Oceanic plates. This is made of basalt. This is thinner but heavier. Thinner but heavier. Okay. See, don't get confused between these two. If you ask me this question, sir, how can it be thick but still be light? Pillow. I take pillow, hit on your face. For a small few seconds, you'll find some irritation. Thinner but heavier. I take this iron rod not iron rod, and the iron sheet will be there, no? Used to cover water tank, or which every house will have something called as water tank, no? Take that iron rod, or what is on the road, take the iron rod, sir. The thickness will be less only compared to pillow. Take and slam your face, you'll be in hospital for 15 days. Okay, don't ask me how thick but light. Either pillow, this is iron sheet. Not the idea. Now let me show you the plate. So continental plate is made of granite. That's why I told you. Igneous rock, write something and keep. Basalt is denser than granite. It's heavy, okay, compared to granite. So just a second, I'll just take the map segment. So that now you become comfortable with mountain ranges, which we saw in map reading class. Hope you remember map reading, people. Now when I recollect mountains, you should be in a position to appreciate it. Right, this should do very well. See, I'm not, I will write the example specifically on the board. This is just to make, before the break, I just want to make sure that you've got the consistency with the subject, because before that, if I give the break, it won't be proper. Now you should be in a position to relate. Do you see North America right here? Okay. See, Pacific plate is actually in convergence with several plates in this area. You take North America and the Pacific plate are actually converging. They're colliding with each other. Because of collision only, you find mountain ranges. Remember, Rocky Mountains, extending from northern portion to southern portion. We saw a convergence, collision, that leads to folding. Fold mountains, right? You take South America, for example. South America, again, you will find collision. Where did I go? Yeah, again, you'll find collision. There is a minor plate here. The minor plate is Nazca. You'll find Nazca Ridge. So Nazca plate and South American plate are colliding. This leads to formation of one of the longest mountain chains in the world. Andes Mountains, again, collision, fold mountains, very extensive. So in this region, you find large number of volcanoes also, especially concentrated in Ecuador, Chile, and all that. That is why I told you when we are discussing about seismic waves, again and again, pointing that Chile is prone to earthquakes, because collision is there will be earthquakes. Got the idea? Let's come to India right now. Motherland. Ayyo. See, India's here. Indian plate, that is Indo-Australian plate, is colliding with your Eurasian plate. Meaning makes sense. That is why you get Himalayan mountains, one of the longest mountain chains in the world again. So wherever you find convergence, okay, those are the regions where you find large-scale mountain systems. You take the plate here, okay, for example, here you'll find Zagros Mountains, which you saw in Iran. You'll find that Arabian plate is actually colliding with Iran. Arabia is a microplate. Meaning makes sense. So everywhere you go, you'll find it. For example, let's take Atlas Mountains. Atlas Mountains are here. Okay, your African plate is actually moving north in this particular direction. It's moving in this orientation. That's the reason you have mountains which is present right here. So through the presence of the mountains, you'll know where exactly volcanic eruptions is. Why is Japan highly mountainous? Why does Japan have large number of volcanic eruptions? Well, let's go to Japan. Look at the position of Japan. You see Japan right there? So this is Philippines and this is Japan. Japan is in collision everywhere. Okay, it's a very small island arc and it's colliding in the surrounding environment. Japan has no other option. 70% of the land will be mountainous. It is highly volcanic prone. It's highly earthquake prone. You see that? Just by demonstrating where exactly convergence is there, plate tectonics solves most of the conceptual problems. You can also have divergence. For example, you take Atlantic Ocean. I showed you, isn't it? The longest mountain chain in the world is not in India, is not in South America, is not in North America. The longest mountain chain in the world is actually under the oceans in Atlantic. This one is the longest mountain chain in the world, because in the entire section, Atlantic Ocean is tearing apart. The sea floor is spreading here. See, as sea floor is spreading away only, South America is pushed towards this direction. It is going and colliding with the Nazca. That's what I told you. Convergence and divergence go hand in hand. You open here, you push South America here. You open in this particular direction, you'll push North America, and then you'll actually collide with Pacific plate here. You get the idea? So both of them go hand in hand. Got it? So with the example, what is convergent margin, what is divergent margin, I will write in the next slide. So I think at least I've given you the idea of what exactly it is, right? So first of all, have patience. Deccan plate immediately started. Deccan Plateau pove kediyadu. Immediately, what about Western Ghats? First of all, Western Ghats is not a mountain range at all. Western Ghats was a plateau. The plateau got broken down into two parts. Reserve your questions, people. Mudikeve plate tectonics. Deccan Plateau, there is one more reason. There is a concept called as intraplate volcanoes. That's how Deccan Plateau is formed. Both the questions you asked were exceptions, not part of plate tectonic theory. Take a break for 5 minutes. I will provide examples, then we'll finish plate tectonic theory. After that, we'll be stepping formally into volcanoes. And after volcanoes, definitely mountains can be done today. Okay, 5 minutes. Is it clear? Both Deccan Plateau, I told you, it's an intraplate volcano. We will discuss under volcanoes. Western Ghats was a plateau. The plateau got broke down. That is how the mountain or hill range was created. It was not created due to convergence or divergence. Okay, 5 minutes. Right. So now we'll need to look at concrete examples. Okay. So let me start. Are mountains formed only by the distortion of the weak plates? No, not exactly. Okay, it's like weak parts of the crust. Wait for mountain building. There is one more type of mountains called as fault block mountain. Okay, that's totally different. Please wait for it. Right. So based on the interaction of plates, different or three types, I'll write it as three types. So three types of plate boundaries or margins. Plate boundaries or margins are created. Full stop. I'll just show you a basic idea before I proceed further. So for example, this is an area where heat is very strong from the asthenosphere, and here you will experience divergence. So this is a divergent margin, divergence margin. You take the other hand where heat is not concentrated. Here you'll see that two plates are colliding. For example, one person is sinking into asthenosphere, the other person is colliding in this case. So two are meeting together. This is conversion margin. Convergence. Just keep this diagram so that this will serve as a reference for the subsequent diagrams which come. So you can have either divergence where heat is concentrated or convergence where heat is actually less. Divergence and convergence. Use the word finished if you're ready. We'll go one by one. First, we'll start with conversion margins. Thank you. Now, first is conversion margins with examples. Conversion margins. See, these are usually characterized by explosive volcanoes. Again, not always, usually characterized by explosive volcanoes, fold mountains, and powerful earthquakes. I will explain fold and fault mountains in the terminal end of the class. We will come across that, don't worry. Just note these terms alone. It will be again repeated over a point of time. So I broadly give you three basic ideas. See, thing is, collision can happen between three different combinations. We can have ocean-ocean collision. Two ocean plates can collide. You can have ocean-continent collision. That is possible. Or you can have continent-continent collision. But three different types are there. See, always remember between an ocean-ocean collision or ocean-continent collision, first we'll address this particular thing. Okay, ocean-continent collision, ocean plate and continent plate, it will always be the ocean plate which goes inside the asthenosphere. Why? Oceanic plate is made of basalt, and basalt is much denser than granite. So ocean plate will sink in. So you can ask me, sir, what will happen if there are two continental plates? What will happen if there are two ocean plates? The thing is, if there are two plates which are of the same composition, then the size matters. Okay, which is having the larger surface area, which means it'll be having more density. So naturally, it'll have a tendency to go down. Meaning makes sense. Ocean versus continent, no doubt. It's ocean moving down. For other plates, it's technically the size. Size gives you more density. Ready? So ocean-ocean example, Pacific plate, ocean-ocean composition will actually create, we write it here, this will create island arcs. Example, you can take Pacific plate colliding with Japan. Okay, or Pacific plate colliding with the Philippines. Japan is a minor plate. Philippines is a minor plate. These are smaller plates. Okay, so Pacific plate is the one who's sinking down. Okay, island arcs. So that's why these are archipelagos, an extension of volcanic islands you'll get. Japan is a volcanic island. Philippines, system of volcanic islands. You take your Indonesia. Indonesia will be in the terminal end. We'll see the map again. You'll find island arcs. Islands which are composed of volcanic eruptions. Ocean-continent collision, you'll find collision mountains. Simplest example, I'll give you North America colliding with Pacific, because that is what is creating Rockies. North America colliding with Pacific. North America is a continental plate, Pacific is the ocean plate. So you'll get collision mountains, the characters. You'll get a very simple fold mountain, something like this. Very simple structure. Okay, you'll never find a very complex folding. Just a simple fold will come. The entire mountain range will be something like this. Consistently, you'll only find one single fold. Got it? What is fold, I will explain later. Just understand we are talking about a very simple concept. Okay, one single line. Now let me talk about a third type, continent-continent collision. See, this is slightly different. The reason being, you will create mountains again. Okay, what type of mountains? Like this will create cordilleran types of mountains. Pardon me? Oh, really sorry. I changed the word. This is cordilleran mountains. Cordilleran is Spanish. Okay. Cordilleran. Cordilleran mountains. Here you'll find collision mountains. Now let me explain the difference. I think if you look at Himalayas, you'll be in a better position to understand, but still, before that. Example is Eurasian plate colliding with Indo-Australian plate. Indo-Australian plate. Now, basic difference, like what is the difference between the first and second one? See, if you ever heard about Himalayan mountains, I know that India map is not over, but you would have heard about several ranges. For example, let me give you certain names. You will know these things. Ladakh mountain range, Pirpanjal mountain range, Dauladhar mountain range, Sivalik mountain range, Great Himachal mountain range, Karakoram mountain range. You get the idea? You will never find a single folded mountain. You will find several complexly folded mountains. That is the difference between a collision and Cordilleran mountains. This will have a very simpler structure. Simple. It's much more simple, the mountain structure. This is very complex. Himalayas are complexly folded mountains. You get it? And point to be noted is, you will find volcanoes here. You will find volcanoes here. You will not find volcanoes here. Okay. Why we will see under volcanoes? Okay, you won't find volcanoes. That's why Himalayas does not have volcanoes, because it's a continent-continent collision. Why, I will explain. Be patient. Please be patient. Just give me some time, I'll take you there. Okay. It is a very simple reason. That's why Himalaya does not find volcanoes. Shall I proceed further? I think with examples you got the idea. Next is divergent margin. Yes. 2 responses. Yes. 3 responses. Thank you. Moving to divergent margin. So divergent plate margins or divergent boundaries. See, in divergent margins, you'll find effusive volcanoes. These are more dominant. See, effusive volcanoes means opposite. They are not explosive. They'll tend to flow. Okay, not very powerful. Not powerful at all. Okay, you'll find less powerful earthquakes. Less powerful earthquakes. And fault block mountains. I will explain fault block mountains under the mountain system. Fold also you'll see there. Is it clear? So examples. So you can either have an ocean-ocean divergence, either have a continent-continent divergence. See, please remember, it is not possible to have OC. OC not possible at all. CO also not possible. You know, one plate, now only one. See, ocean plate is there, I will split ocean plate apart. Continent plate is there, continent plate I will split apart. I can't split ocean and continent because they are already separate. Only 2 possibilities are there. Example, you find ocean-ocean divergence properly recorded in Atlantic Ocean, and continent-continent divergence, best example is seen in eastern part of Africa, East Africa. Africa is actually splitting open. I will be in a better position to tell you, wait for it. Under mountain building, like technically you will find 2 Africas. I'll show you the diagram maybe. What is the idea? Africa is here. Hold on a second. Let me just show you the diagram. Africa's physical map. Even though we will discuss in the mountains, just the basic idea. Right there. Africa is splitting open. This region. Okay. This split is stretching far north. After a point of time, Africa will split into two continents. See, this rift which you see right here is actually part or was part of Red Sea. You see Red Sea right here, isn't it? Let me just zoom out. Red Sea. Red Sea is actually recently formed sea. It was actually closed in this case. Now, I think if I draw the plate tectonic diagram, it will be sensible for you. See this? Red Sea is there? No. Red Sea actually opened this way. Not the idea. Only after opening between these two regions, your Red Sea was properly created. Before this, the land area was actually closed. Got it? Similar to that, Africa will become something like this. You'll have the African continent. The Rift Valley is concentrated on the eastern side. So this will slowly break open, and in future, it will create an African Ocean where you'll find a West African continent, East African continent, an African water body of ocean will be there. Only thing is, we won't be alive to see this because this is going to happen over millions of years. This will happen in the future. So, continent-continent divergence, Africa is an example. I am not bluffing. It is true. Okay. Got it. So, this for ocean-ocean divergence. Sorry, continent-continent divergence, ocean-ocean divergence, Atlantic Ocean we've already seen. Last one. Yes, I haven't told you about one important plate margin, even though it plays an important role in certain countries. See, plates can either diverge. Plates can either converge. Plates can also do this. Two plates are there. This is possible, no? I'm not doing it well. Sliding past each other, not necessarily I'll need to converge or diverge. If two plates are there, or let me use my hands, much more easier for me. They can either converge, they can either diverge, or two plates are there. Plates can slide past each other. That is called as transform margins. Transform boundaries. Transform boundaries or margins are usually not associated with volcanic eruptions or mountain building Stop. Okay, because see, where will your volcanic eruption come? Land area is close. You need to split open for your volcanic erupt. So that's not possible at all. Mountains also, elevation needs to be there. You need to at least raise over 700,000 meters to create mountains. That is also not possible. Even if there is a slip, it doesn't get beyond few hundred meters. So both are not possible. The folding or faulting concept doesn't happen here. But they produce some of the most powerful earthquakes. Some of the most powerful earthquakes. Example, San Andreas, California. San Andreas in California. California is actually a transform margin. California is sliding part of the Pacific. So technically, California is a dangerous place to live in terms of geophysics, in terms of your physiological characteristics. The reason being, you're exposing yourself to one of the most powerful earthquakes in the world, but ironically, Silicon Valley is in California. And ironically, Mediterranean climate, one of the best climates in the world is in California. So give or take, okay? Some parts of the world are good, at the same time bad. Dwayne Johnson. Oh, San Andreas. People. San Andreas, Dwayne Johnson. Okay. So now I think you're ready. So since the basic idea is given, and since at least you got an overview, I think we can go for specific parts also. We'll take volcanoes right now. We'll start from volcanoes. Pretty sure volcanoes can be done. And then we'll stretch to mountains also. At least 4 mountains we'll try to finish. Ready? Volcanoes. See, because once this section is done, volcanoes, mountain building, earthquakes, then it's over. Okay, geomorphology will only have one more concept called isostasy. Then I'll just need to give the introduction for your weathering, erosion, mass wasting. Then so next class, possibly half an hour, I'll finish geomorphology. I can step into oceans. This is the most important topic for you. Volcano. So you take any textbook, defining volcano will be a problem because still today, geomorphologists are having trouble. Should I describe volcano as a mountain from which lava erupts, or should I describe volcano as a hole? Because at the end of the day, even if you have something called as a hole, and if materials kind of reach the earth crust, then also you can call it as a volcano. So how should I define a volcano is up to debate. So I will take the second definition because I feel it is more relevant. Okay. Volcano is an opening on the earth's surface, which facilitates the movement of lava to the surface. Their distribution is closely linked with plate margins, both convergent and divergent. Okay. Waiting for Black Adam. Volcano is an opening with the on the Earth's surface which facilitates the migration of lava to the surface. The distribution is closely linked with plate margins, both convergent and divergent. See, if I'm going to ask you a mains question, two possibilities. Provide an account of global distribution of volcanoes. That's one. Second is, how is volcano associated with plate tectonics? If you can answer the second question, first question is fairly easy. You got the idea? So if you look at volcanic distribution, 95% of volcano distribution can simply be explained through plate tectonics. We'll go one by one. I'll give you like hints, okay? Convergent plate margin, how exactly should you be writing? Hope you're ready. I'll reread it one more time, then flip over. Volcano is an opening on the Earth's surface which facilitates the movement of lava. The distribution is clearly associated with plate margins, both convergent and divergent. Moving further, convergent margin. Volcanoes in convergent margin. See, the process is fairly simple. Now, once I finish this, you'll understand why Himalayas does not have volcanoes. Listen carefully. When there are two plates colliding, okay, we'll take for simpler understanding, I'm taking an ocean plate and continental plate. See what happens. The ocean plate is much denser, so he's going to sink inside the asthenosphere, right? It's very thin. The continental plate, on the other hand, is going to get folded. He's very weak, he's getting broken and fractured. Okay. Space constraint. The thing is, when the plate is entering the asthenosphere, this is the asthenosphere. It's not that only the plate is going to enter. If this is going to be my ocean plate, this is my continental plate. Over the oceans, you have large volume of water. And not just water. Ocean has a good concentration of deposits also. Let's think about what type of let's think about what type of organisms live in the oceans. You take mollusks, you take echinoderms. Large number of them have shells which are made of calcium carbonate. So the ocean is rich in both water and calcium carbonate. So when the asthenosphere is slipping into the oceans, along with the ocean plate, you will have water entering. Okay, water is entering, right? You will have carbonate deposits entering. I'll write it here. That's easy for space. Carbonate deposits. So that is also going to enter in to the asthenosphere. Now, once you put water here, the boiling point is only 100 degrees Celsius. And asthenosphere has radioactive elements. So eventually, water will get converted to water vapor. So this is in vapor state right now. Vapor state. You take carbon deposits, once they enter asthenosphere again, they will get vaporized. You will create carbon dioxide gas. See, this buildup goes on for a very long time, consistently over a long period of time. And this section, you already know the continental. See, I showed you know two plates are colliding. This guy is weak. That's why he's getting folded and fractured. So once this person is fractured, this pressure will build on over a long period of time. So buildup of hydrostatic pressure. Hydrostatic pressure. When the hydrostatic pressure exceeds a certain limit, through fractures available, all of a sudden you'll get volcanic eruptions which are heavily explosive. This is the reason you get volcanic eruptions. So that is why you will find volcanoes in ocean-ocean convergence. You'll find volcanoes in ocean-continent convergence. Both the cases you find water and carbonate deposits. Continent-continent convergence, not possible. How will you create it? Because you don't have water. This is why Himalayan mountains do not have volcanoes. A simpler answer. Meaning makes sense. So these are the hints. So conversion margin. Okay. Movement of large volume of water. And carbonate deposits. In the asthenosphere. The vaporization, let me write it here itself. Okay. The vaporization builds up hydrostatic pressure. Hydrostatic pressure. Explosion or explosive volcanoes are created. Now I need to go to world map to tell you about distribution. Why explosive volcanoes are mostly around the Pacific Ocean. Okay. Use the word finished if you're done. We'll go to the world map right now. See, if climate was a certain flavor, geomorphology is a different flavor. Okay. Every segment of geography has their own speciality. You ready? Yes, thank you. Now this map is constricted. I was not able to zoom in properly. Let me find. I'll just find a world map. Hold on. I was not comfortable with. Why is this app open? Not needed. Okay. Yeah. I think. Okay, this would do. I think so. No. Okay, this would definitely do. Right. See, the reason I wanted Pacific Ocean separately is that 65% of all the volcanoes which you find on land area is actually found in areas surrounding the Pacific Ocean. The reason being, everywhere there is convergence. For example, you take your North American continent converging with the Pacific. Okay, so naturally you'll find large number of volcanic mountains here. So Pacific in collision with Japan, volcanic mountains. Pacific in collision with Alaska. You find a group of islands here called as, later you check in your map, called as Aleutian Islands. I'll write the spelling here. A-L-E-U-T-I-A-N. Aleutian Islands. This is part of Alaska. Got it? Here also you'll find volcanic mountains. It's technically an island arc, ocean plate. Collision. You take Philippines. The Philippines is right here. Collision. So here again, you'll find volcanic eruptions. See, one country which is actually able to escape out of this entire problem is Australia, because you take New Zealand. This is New Zealand right here. I think able to visualize this. So New Zealand is right here. In New Zealand, you'll have volcanic eruptions. In New Zealand, you'll find fold mountains. Australia escapes. Got it? Australia is right here. This is not in the plate margin. The plate margin kind of extends like this. This entire area will find a complete volcanic chain. Okay, you'll find your Nazca plate, yeah, somewhere around here. This will be my Nazca plate, and there you might find certain parts of divergence also. But apart from that, mostly there is convergence in all the sites. You take Australia, Australia is actually sitting inside the plate. See, person who's sitting at the edge only will face a problem because he's actually under collision with Pacific. I am sitting here. I have no issue at all. Now, this puts Australia at a disadvantage. If you don't have volcanoes, point is, you will not find good volcanic ash for your soil. This region is called as the Pacific Ring of Fire. Ring of Fire. This was asked in this year's mains. Most of the students, even optional students, made a mistake. You know why? They use this word, circum-Pacific belt. Both mean the one and the same thing. Surrounding Pacific, that's all. Circum-Pacific belt. The question was, describe the geophysical character of circum-Pacific belt. People are, geophysical. Geophysical is nothing. The word is there in the syllabus. That's why we tell you learn the syllabus properly. Geophysical character, you need to talk about volcanoes, mountains, earthquakes in this region. 10-mark question. Simplest one. Optional students made error. Geo-optional. Keta, I didn't teach. Ama, I didn't teach. Why is divergence not possible between CU? Why is divergence not possible between CU? But I'm simple. Listen carefully. Chapati is there. Chapati, I tear 2 chapati. Dosa is there. Dosa, I tear 2 dosa. Idli is there. 2 idli, I'll separate. I cannot separate idli and chapati. I cannot separate dosa and chapati. Meaning makes sense. Now did you understand? Man, is it okay? Why divergence is not possible between chapati and that's all. In the level of Sonada. Shall I proceed to the next one? I think you got the idea why Pacific is called as Ring of Fire, also called as Circum-Pacific Belt. 65% of volcanoes on land is present in this region. I'd like to take you to second region of importance is region surrounding Indonesia. This one again. So this is a convergent margin. So this particular region here again. So Philippines and Indonesia. This region will find large number of volcanoes. So here is again where you find convergence. This is where your Indo-Australian plate is colliding with this particular region, islands of Indonesia. This is the region where you had your tsunamis in 2004, December 26. Why tsunamis? What are tsunamis? We learn under oceanography, but just know that it's possible again in convergent plate margin. Meaning makes sense. Third important region after Indonesia. So region 1 is Circum-Pacific Belts. Region 2 is Indonesia, high concentration of volcanoes. Third region, and possibly these 3 regions alone have 90% of all volcanoes in the world. Third region is here. Quite unexpected, right? See where I'm zooming in? This one. Caribbean Sea. Because Caribbean is actually a minor plate. This is a minor plate. Okay, and it's actually in collision. Okay, with these regions. So here, Caribbean plate. Caribbean plates is in a convergent margin. So your Indonesian region, and after your Indonesian region, your Caribbean region. These 3 regions alone have close to 90% of all volcanoes on land areas. Got it? 3 regions. Region 1, Circum-Pacific. Region 2, Indonesia. Region 3, the region of Caribbean. Moving to the next part, divergence. So convergence was quite easy, isn't it? Divergence also same phenomenon. Divergence. See, here the mechanism is more simpler because in this case, same plate is there and the plate is getting split open, that's all. Why? Because of radioactive heat. Got it? So because of constant heating from the bottom, you pierce this region and then move out. Is it clear? So let me write the description here. Divergent margins. Margins experience constant heating. Experience constant heating which melts the crust. Which melts the crust. The release of pressure, the release of pressure reduces the melting point, and magma flows as lava. You should be in a position to make sense of the second statement. I hope so. Okay. Read the second statement again, you'll get the idea. I will explain in a minute or a few seconds. The discussion we saw in the Earth's interior. I think you remember. Okay. With increase in pressure, there is always better boiling point and better melting point. See, if I constantly keep heating from beneath, okay, I'm going to melt this area. So slowly what I did, if you remember, is I reduce the pressure. See, weight is placed on my head. I heated this region and then removed the weight. Once I remove the weight, I'm removing the pressure. I remove the pressure, the melting point will immediately decline. So this ductile material, again and again we are saying, is kind of molten material. Once you reduce the melting point, it will easily melt. That is why I told you it is flowing. Lava flows outside. It doesn't explode because there is no buildup of pressure. Pressure is getting released on the opposite. That is why conversion margins of explosive volcanoes, they have effusive volcanoes. Effusive means to flow. Effusive, to flow. Okay, because you're reducing melting point. You're releasing pressure. You make it easier for them. Got it? Use the word finished if you're done. The last concept for volcanoes we will see. Now Deccan Plateau will come into picture. Okay. Right. Thanks for the response. See, as I told you, 95% of volcanoes in the world can be explained either through convergent explanation or divergent explanation. This example, you can look at this region itself. I mean, your entire Atlantic Ocean, this entire region will have volcanic mountains. Everywhere there are volcanic mountains. Okay, underwater volcanoes. Okay, and one more point I just want to add. This is trivia, general trivia. Know this: the number of volcanoes which you find underwater is much higher than the volcanoes on land. First reason is 70% of the world is dominated by water bodies, and this is a consistent volcanic mountain chain. Like, this is not visible. That's all. This extends as far as Iceland. Iceland is right here. Got it? And when it comes to a small percentage of volcanic eruptions, we are not able to really fit them into plate tectonics theory, either as convergence or divergence. For that only, they came up with a concept called as mantle plume, which creates hotspots. So let me write that. A small percentage of volcanic activity cannot be described through divergent or convergent margins. Divergent or convergent margins. Convergent margins. Full stop. This is explained by the theory of mantle plumes. It creates intraplate volcanoes. Take this down. Next slide, you'll get explanation. A small percentage of volcanic activity cannot be described through either margins. So this is explained by the theory of mantle plumes. What exactly are they? I hope you're ready. See, again, before explaining mantle plumes itself, I'll tell you this. Similar to the magnetic pole flip, here also you'll not find convincing explanation. It's more of a fixation to explain, this could be the reason why things are actually happening. Ready? Composition of the Earth's interior: core, mantle, and then the crust. Crust, mantle, and then the core. Okay. So to explain this intraplate activity, okay, we only have a theory which states that from the core mantle boundary, you're talking about heat rising up. I'll write the statement, no worries. Core mantle boundary, you have heat slowly emanating and moving up. Is it clear? Once this heat moves to the asthenosphere, this asthenosphere is triggered because it is receiving more and more energy. So naturally, you will have a volcano erupting on top of the crust. Meaning makes sense. So two questions need to get answered. Why only in specific parts of the world do we have this heat transfer? You do not understand. And second thing, you need to always keep it in mind, there is no pipe connection. It's not that intraplate volcano is there, you can open it and then jump inside. Not possible at all. This is not a pipe. We are talking about heat transfer. And let me tell you one more thing. It's through a very slow process of solid convection. And you did hear me correctly. Whenever we use the word convection, we use it for fluid systems for heat transfer. When I say solid convection, it means the particles are moving. It doesn't happen in a solid medium. It's an extremely, extremely slow process. See, think about this. If you're actually conducting and if there is very good amount of heat, mantle will melt. Once mantle melts, you will fall down. The crust will melt after a point of time. So mantle reorganizes itself, allowing the heat to pass through. Extremely slow process happens only in certain parts of the world. And understand one thing. It works like this. Hold on a second. Double paper. Make it single. As long as it's not a relationship, it can always be broken. Just a piece of paper. Plate is there. Sorry. Plate is there. Core mantle. Plate is there. Core mantle boundary, heat is emanating outside. Okay. Slowly this area will get heated. After heating after a point of time, this will actually break this area and come out as volcano. Meaning makes sense. Hold on. This heat operation is consistent over long periods of time. Got it? But plate is not consistent, plate is moving. So, volcano created. It will still be heating in this area. Thing is, plate will move. Let's say plate moves after points. After the plate moves, it will stay there for some time, it's again getting heated. After a point of time, second volcano will come. Okay, this will create one more island. After a point of time, plate will move. Thousands and millions of years. Then third volcano will come. Fourth volcano will come. The area of operation is small. But after a point of time, if you look properly, hole is there and nothing is visible. You will find a series of volcanic eruptions. 1, 2, 3, and 4. So due to constant motion of plates, if the mantle plume is consistent, it can actually create several hotspots, which are volcanic islands. This is true for India also. I will I'll tell you how exactly India is related. You'll find that there is a chain of islands related to India also. Best example for understanding this is Hawaii. So let me write that. Waste of paper. Okay. Mantle plumes are a result for very slow process of heat transfer from the core mantle boundary through solid convection full stop. This creates hotspots of volcanic activity when plates move a series of volcanic islands can be created. can be created. Full stop. Okay. I think now we're getting the grip of that, what exactly it is. Like, I'll show you two locations. One, I'll show you Pacific Ocean, and then second is India. Okay. Several hotspots are there. May point out major hotspots, but I just want to show the chain aspect also. That's why. Use the word finished if you're ready. Okay. This segment is not there in NCRT. The NCRT is more concise. That's the only thing. It doesn't talk about things in detail. Thank you for the response. So now let's go to the... I need to give you one more diagram, but let me show the map and then I'll come back here first. Hotspots. No. We'll go for mantle plume map then. Yeah, this is good. Is several places on Earth where islands are actually created as a result of mantle plumes. One of the important films, if you recollect, is actually 2012. And in 2012, they talk about mention of Yellowstone National Park. Yellowstone National Park is an interplate volcano. You can see the location right here. It's not really present in any margin. Margin is right here, where you see the line, where you see those blue color triangles and all that. Those are areas of conversion. This is way in. Got it? Let me tell you one more island which you're familiar with. You take Iceland. See, Iceland, there is double whammy. You see that? Iceland is already sitting on a divergent plate margin, which means there is more volcanic activity. At the same time, Iceland is a hotspot. This is why Iceland is world leader when it comes to geothermal energy. 90% of electricity needs and energy needs in Iceland is simply used by geothermal energy. There is immense amount of potential because you just put in water through your ground, it comes back as steam. Large number of hot springs. Very beneficial for Iceland. Very good form of renewable energy. Only in certain parts of the world you'll find it. Okay. You take these islands, which you will find in the Atlantic Ocean. This is not part of a convergent margin. Divergent margin is here. This is divergent margin. For example, Azores Island, Canary Islands, Cape Verde. Like, these are important ones. Do you remember this? This we saw in map reading class. Galapagos, off the coast of Ecuador, where Charles Darwin did all his observations, which leads to his origin of species. Galapagos Island, hotspot. And now let me show you. Yeah, this is what I want, but I will show you in the bigger map. So this is what we are concerned about. Reunion Island. Okay, why Reunion Island? Reunion Island is very important for India. Currently, this island is held by France. But once upon a time, India crossed over this region. I'll tell you what happened. Okay. So the thing is, this used to be the structure. Since plate tectonics is over, like Gondwana land, you had Australia, Antarctica and all that, and India was part of the eastern segment. After breaking open from the African continent, this would happen. Like, you had your Africa. Madagascar was a strip of landmass which was actually between Indian subcontinent and African. Madagascar stayed right here. India began to break down, and the triangle started moving towards the eastern side. When it moved over this area, it came under the influence of this reunion hotspot. Okay, and this reunion hotspot started pumping large amount of lava over India, spreading over several acres. Meaning makes sense. Do pay attention. If you look at the time period, when exactly it happens, it's approximately 67 to 63 million years ago. Talking about close to 3.5 to 4 million years. And it was not a single volcanic eruption which happened over India. It was several layers. So if you go into create several layers of volcanic eruption, so you get a one layer of volcanic eruption. Okay, then few 100,000 years, again lava begins to deposit, and again one more layer, one more layer, one more layer, one more layer. You get that? So that is why you created a step-like structure when it came to your central Indian region. The step-like structure is called Trepin. Step-like, steps, Trepin. It's from this word Trepin that the word Deccan trap is derived. Trap. You got it? That's how the word Deccan trap comes in. And one more information, not for exam perspective, but you should know this as part, not just general trivia, just general information. Look at the time period. 66 million years ago, an important event happened. Can anyone tell me what happened 66 million years ago? What happened 66 million years ago? Something happened. Something like Basha. Very good. Extinction of dinosaurs. Very, very good. See, actually, it is believed one of the major reasons, there are several theories for extinction of dinosaurs, but one of the theories states that the explosion, which was from the reunion hotspot over the Indian subcontinent for close to 3.5 to 4 million years, was one of the major reasons for extinction of dinosaurs. Reason being, see, volcanic eruptions will change your atmospheric composition. You have consistent volcanic eruptions, you have dark clouds hovering in. So large number of clouds will reduce insolation. It's not possible for your sunlight to penetrate in because dust clouds will actually block your sunlight. So which means there is reduction in temperature. Photosynthesis will get affected. If photosynthesis gets affected, then naturally if an animal is going to consume plants and live, it is going to die. The entire ecosystem collapses. Plants die, then producers are destroyed, primary consumers destroyed, then the ecosystem gets affected. And these were tertiary consumers, many dinosaurs. Okay, you take T-Rex. T-Rex is a very important predator. You get the idea? So it's considered as one of the reasons for the extinction of dinosaurs. Now, I'll show you one picture, and after the picture, I'll show you the physical map. Ready? So I think you got the idea, Trepin and all that. So I think now your question on Deccan Plateau is convincingly answered. Someone asked me some time back. So let me close this. This is fine. I want to talk about this region. Mauritius. You find something called as Chagos Lakadavi Ridge, isn't it? Maldives. It will extend as far as western part of India. This entire chain is actually connected. They are related. Okay, everywhere there were volcanic eruptions as the plate kept moving. This is one example, consistency. Or starting from Mauritius. So Reunion is right here. This is Reunion Island. So starting from Reunion as far as western part of India, you can see the connection. Okay, Reunion Island, Mauritius, Mauritius and Maldives. And north of Maldives, you find India. One more example is right there in Central Pacific, Hawaiian Islands. Hawaii, you have close to 100 plus volcanic islands consistently in the same direction. Later, you look for the structure of Hawaiian Islands, it will be in one central direction. See, Pacific Ocean, Yedzile can have volcano. Here, there is a conversion margin. This is center of Pacific Ocean. Center of Pacific Ocean, no margin is there. Perfect intraplate volcano example. So you can quote India or Hawaiian Islands. Both are well-versed, consistent examples. You know, a chain will be there, actually. So when you draw the diagram in exam, just draw this. This will be fine. This one. Just say plate is there. Mantle plume is operating. Mantle plume. And due to mantle plume, there is creation of volcanic islands. Okay. Over a period of time, as the plate is moving, plate movement. Okay, this mantle plume is able to funnel more. Is it clear? And you get a chain of islands. So you get several islands. 1, 2, 3, and a new one is getting created. Okay, so this diagram will suit for exam, a smaller one. Okay. Narkandam volcanoes in Bay of Bengal. No, it's not technically intraplates. Okay, two questions are from the same thing. See, the volcanic islands which you find in Barren Island, it's part of your volcanic, it's part of your Himalayan mountains closest, the Tethys Sea is getting close. There, water is not available. But once you go there, there is Himalayan mountains. I think the question is answered. It's Andaman and Nicobar is technically extension of Himalayas. Okay, the only difference is in Bay of Bengal, water is present. Presence of water leads to opportunities. Is it clear? So at the end of the day, it boils down to hydrostatic pressure. I think now your questions on volcanoes should be properly answered. I just want to show one picture on Deccan Trap so that you get the idea of layers, the trap section clear, you know. Even if the discussion is done, before I introduce fold mountains. See, fall block mountains time won't be there, but I'll definitely finish fold mountains. It's a small topic only. Since you've understood the topic, it's much easier for you to follow. Hold on. Just one picture on Deccan Trap so that you appreciate what you've learned. Uh, yeah, very good picture. Look at this. I was talking about step-like structure, isn't it? Layers and layers of deposition. And this is what you're talking about. So you can clearly see that every particular structure, you clearly see those black color strip brands. See, this is not sedimentary rock. I'm not talking about sedimentary rock. It's not coal deposition. This is volcanic basalt itself, basalt depositing over layers and layers. You'll find these structures at several places in Maharashtra and Karnataka, and Gujarat also. Now, parts of Gujarat, not entire Gujarat, this is a perfect example. This is Ajanta Caves. See, Ajanta Caves and Ellora Caves, the two UNESCO World Heritage Sites in Maharashtra, is actually carved over Deccan Trap. Without Deccan Trap, these monuments could not be constructed. Just a reference to culture. Okay, that is why if you look at Maharashtra will find several Buddhist sites. Relation with art and culture. Later when you learn art and culture, or maybe, I don't know, maybe ancient India is done, you will find that there is good monumental present. Why monuments are present? Because that is where you find your rock structure. Only when rocks are present, you can carve them in. Rocks are absent, you cannot do that. So one relational point with history, since it is general studies, paper 1. Okay. Can you see Hawaii is this? This is Hawaii. This is technically Hawaii. So you have a mantle plume in Hawaiian Islands, and as the plate moved, you create a series of volcanic islands. The point which I wanted to add is, usually you cannot have islands in the center of, you cannot have volcanic eruption center of Pacific, because Pacific is a conversion margin everywhere. Atlantic Ocean, you can have volcanoes, because Atlantic is divergent, volcanoes will come. So only by using mantle plumes, you can explain formation of Hawaiian Islands, which is there in the center of Pacific Ocean. I just wanted you to look at the picture of Hawaiian Islands later, a satellite image. You'll find that all the islands will be, you will see that it's kind of moving in the same direction. Like, not, they'll have this southeastern to northwestern orientation that indicates plate movement also. That's the point which I wanted to add. Problem is, if I start with mountain building, see, I'll just finish fold mountains alone. It'll only take 5 minutes, then I'll take queries, okay? Just fold mountains alone. Is it okay? Next, we'll go to mountains. I'll tell the first type. First type is very easy. Fold mountains. First, mountains. Landforms with the elevation of more than 1 kilometer, broadly divided as fold mountains and fault block mountains. Fold mountains and fault block mountains. That's why, map reading. All these places, if I did not introduce earlier and suddenly you learn these places, then it might be very difficult. So you sow the seeds, you reap it very late, but still you reap it, right? I don't know, it's been like 6 months since map reading. I don't remember, at least 5 months. We're in January right now. 3 months, 4 months, I don't know. I'll read it and then proceed to the next page. Landforms with elevation of more than 1 kilometer, broadly divided as fold mountains and fault block mountains. I was keeping a very simple suspense. It's not even a suspense. Fold mountain, fold mountain. I never told you what is a fold, isn't it? Nothing. Fold is a wave-like bend. Wave-like bend on the earth crust. Earth crust caused by compressional forces. That's all. Compressional forces. So if you find something like this is a fold. That's it. The normal mountain which you're drawing. Fold is just a technical term. That's all. Fold means a wave-like bend. wave-like bend on the earth crust formed due to compressional forces. If this wave-like bend has an elevation of more than 1 kilometer, you will call it as a fold mountain. So, okay. The next diagram will be simple and similar to your volcanics, the explosive volcano. That's why I told you this can be easily done. I'll wait for some more time, like few more seconds, then I'll flip over. I'll read it again. Fold is a wave-like bend on the earth crust caused by compressional forces. If the fold is more than 1 kilometer, you call it as a fold mountain. The greatest example, Himalayan mountains. Rockies, Andes, Alps, Atlas, all of them. Ready? Here it goes. So similar to the previous discussion, two plates are colliding. Denser plate sinks into asthenosphere. The weaker plate is folded. He's squeezed and crushed because he doesn't have strength. Okay, so convergence. Yeah, this will be better. Convergence. So high compressional force. Compressional force. So this is my lighter plate. Lighter plate. Got it? So I'll write the description here. Along convergent margins. Convergent margins. The compressional forces. Compressional forces modify the structure of the plate. Modify the structure of the plate. Continue. The lighter plate. The lighter plate is squeezed and folded into mountains. Full stop. Example, Himalayas, Rockies, Andes, Alps, Atlas. Anything? How many more classes for geography? 3 more classes. Okay, 3 more. Like next session, I'll be extending fault block mountains. Earthquakes should take 15 to 20 minutes. And then isostasy, it's a very small topic. After that, I'll start with oceans. Oceans, I need half a class, then 2 more sessions. So 3 more sessions for world geography. Indian geography, possibly 6 or 7. Okay. So 3 plus 6 is equal to 9. Okay, so that ends the discussion for today. I'll hold here. Slides, no worries. Slide numbers, no worries at all. I will save the slides and send it to you. So if any questions are there, please put up your hands or raise your hands. I'll ask him to enable. Okay. Do hand raise. Hand raise and enable. So today I think you had several questions answered. Because topics like interior of the earth really doesn't answer several questions. But once you take volcanoes and mountains, I think you will feel comfortable. In certain parts of the world, some things we might have skipped in climatology, you should be in a position to make connection. Why Rockies, why Andes and all that. Once we finish oceans, the world will be in your hands for sure.
Hello, sir.
Yes.
Hello.
Yes, go ahead. Yes, you're audible.
Can you explain? Yes, sir. Can you explain again North American plate and Eurasian plate divergence and convergence concepts, sir?
North American
map.
North
American plate, Eurasian plate, Nazca plate, convergence and divergence. That slide, sir.
See, I'll take the map. You'll tell me where the doubt is. Hold on a second. Let me open the map. Where is my world procedure? Okay, closed it. Hold on a second. Stay with me.
Again, sir.
No, hold on a second. Just stay with me. I'll open the map. Wait.
Sure, sir.
See, Indo-Australian plate is in collision in this region. That's not the right way to draw. Hold on a second. Myanmar, Andaman Nicobar, Sumatra. Got it. So this is actually colliding with Eurasia. That is why you have complex folded mountains of Himalayas. Got it? Tsunami is actually in an area of convergent margin where Sumatra is present. This segment is okay. This is okay.
Okay, sir. Okay.
Wait. I'll go step
North
by step.
American plate.
Wait, man. I'll go step by step. This is okay or not?
Okay. Okay, sir.
Next. Atlantic Ocean is divergent, pushes it out. North America is in conversion with Pacific. Rocky Mountains. Is it clear?
Okay, sir.
Okay. Same thing in South America also. Mid-Atlantic Ridge. Divergence. Pushing South America. Nazca's here. Collision leads to formation of anti-mountains. Is this okay?
So this is also convergence, right?
Yeah, this is convergence. This is divergence.
Okay, sir. Clarified. Thank you.
Okay, you want mains test for at least 1 hour before March. Fine. Geography topic. No, see, I'll finish it in 2 weeks' time. Okay, next weekend I'll pretty much wrap it up. I'll tell them to have a mains test. Please explain why Australia does not have volcanoes. Simple, Mr. Lalit. See, Australia is not in a conversion margin. See, I'll tell you, this is my margin. Wherever there is margin only, you will actually have volcanic activity. Correct? New Zealand, there are volcanoes. Australia is sitting here. Here you don't have, see, luckily for Australia, there are no intraplate volcanoes also. Margin is also not there. Intraplate volcanoes also not there. Australia won't experience anything. This is the margin. Australia is not anywhere. You get the idea? So this is the margin. So Indonesia has volcanoes. New Zealand has volcanoes. I'm sitting in the center. No problem. That's why. Anything else? See, you better come through audio. It's much easier to converse. Oh, Northern Lights. Okay, fine. I told you I'll explain the topic at the last. People, auroras are these. Okay, those who wanted to know about auroras, I told you I will explain at the last. See, very simple. See, Earth's magnetic field creates something called as magnetosphere. This is how the magnetosphere is. You will ask me, sir, why is the Earth's magnetic field extended in one area and shortened in one area? So the reason why the Earth's magnetic field is neatly strung towards one section is because of the power of the sun. The sun is extremely powerful, and because of solar wind radiation, the magnetic field is not extended, it's usually closed. See, the hottest portion of the sun, the photosphere, which is actually there in the center, there in the exterior of the sun, releases large amount of high energy particles. Here you're not talking about solid, liquid, gas particles getting emanated. We're talking about plasma. Okay, very high plasma discharge, high energy photons will be emitted by the sun. Usually when these photons or high energy particles are emitted, the geomagnetic field will be strong enough to stop them. Usually, that is why it is strength. The strength is actually getting reduced here because it is blocking something. Now, rarely, plasma discharge is very powerful. They'll be able to break the magnetic field temporarily. They can never replace the entire thing and reach the equator, not possible, but temporarily you'll get a fling. Thing is, once you break it down temporarily, it's these charged particles get trapped in the Earth's magnetosphere. You know Abhimanyu? Abhimanyu is considered by several, or at least by few people, as one of the greatest warriors in Mahabharata. Abhimanyu knows to enter the Chakravyuha, but Abhimanyu does not know to exit the Chakravyuha. These charged particles of photons is similar to Abhimanyu. They will enter the magnetosphere, but they do not know where to exist. And the only direction where they can be passing through is along the direction of the magnetic field lines of force. They will usually pass along the magnetic field lines. Got it? Once they pass along the magnetic field lines, the highest concentration is either there towards the North Pole or South Pole, because that's where the bar magnet is tilted now. Bar magnet is usually either like this or it is like this. Meaning makes sense. So close to North Pole or close to South Pole, your charged particles will go. Composition structure of atmosphere: troposphere, stratosphere, mesosphere, ionosphere. You got the idea? So in ionosphere, these charged particles will come and interact with nitrogen, will come and interact with oxygen. They will add more energy. They'll provide more energy to nitrogen and oxygen. So I think you know this already. Once you provide energy, the atoms will get excited to a higher energy level. When you jump from a higher energy level to a lower energy level, you will release colors. This is what is seen as auroras. This is the reason auroras are concentrated only in the North Pole and South Pole, usually not found in the temperate or tropical region. Usually, we have extremely rare instances where if the plasma discharge is extremely strong, you can find auroras maybe in temperate or tropical region, but mostly concentrated in North Pole and South Pole, because that is why the magnetic field lines are very strong. Okay. There's one question. I think you got the idea. Geomagnetism. Two more questions are there. Volcanoes in Atlantic are effusive as they are formed from divergence. Right, you're right. Volcanoes in Atlantic are effusive. Raising hand is not visible. Rishi, you said world's longest mountain range is in Atlantic. Atlantic is divergence, which means effusive flow. Then how can it lead to mountain ranges? Rishi, it's only a question of time and accumulation. That's all. Actually, maybe if the second concept was clear, I just introduced fold mountains. No, what you find in your Atlantic Ocean is fault block mountains. See, visualize this. I'll just draw the diagram. Like if you have divergence, okay, it's not that the material is going to get deposited only for this layer. Again, I'll have the next layer, I'll break open this and then effuse out. Second layer, third layer, fourth layer. See, you consider something as a mountain once they reach an elevation of more than 1 kilometer. We are not talking about tallest mountains. We are just talking about mountains. That's it. Okay, over a period of time, it'll slowly build. Layer after layer, layer after layer, but it's never explosive at all. Okay, at least mostly not explosive. Because it's not technically based on pressure. You got the idea how I create mountains? Rishi, I believe it's okay. Okay, it's not about very tall mountains. It's all about consistency. Layer by layer, just like how you build Deccan Trap. Layer by layer, you start building, eventually increase the elevation. It's a type of mountain called fault block mountains, okay, which you find in Atlantic. So it's all about how much material you provide. More material, more basalt. More basalt, more solidification, more rocks. Is it okay? This doesn't follow paleomagnetic concept. See, please understand this. How do I explain further? Hold on a second. I think I can flip over. Several years deposition. A very a consistent volcanic eruption moves things out. Okay, so I should be using yellow color. Fine, I'll use blue. I think you'll understand. How was it? Second layer. Okay, third one. Moving far away. You get the idea. The point is, you took the last terminal layer. You'll never find a structure which is flat. You get the meaning. You'll find a structure like this. You can have magnetic strips like these, man. Rishi said, okay, now what I'm drawing with elevation. Is this okay? You can have seafloor spreading. Magnetic strips does not mean the land is flat. You get it? Now is it okay? Section 1, section 2, section 3. Now I think you got the idea. So when we saw magnetic strips, it doesn't mean that the elevation is 0. But anyway, good question. I think at least if anyone had doubts, their doubts would have been clarified. Good linking. Okay. That's the last one. So shall I close the class? People let me know. Next class, we'll finish geomorphology and start with oceans. Fine then. When will we discuss El Nino, La Nina? El Nino, La Nina will be discussed in oceanography class. Boundary between North American plate and Eurasian plate experience convergence or divergence. See, I have a trouble with this question because there is no... See, I'll tell you the problem with the question. You're actually conceiving North America and Eurasia are actually related. See, look at this. Eurasia is here. This is Eurasian plate. Correct? In between Eurasian plate and North American plate, on one side, Pacific is there. There is convergence, which means these two are not related. On the other side, divergence is there. That's why I'm kind of fumbled by the question, why do you ask North America and Eurasia? One side there is divergence, one side there is convergence. One side Atlantic is there, one side Pacific is there. You get my problem? I think at least this diagram should be clear. There is convergence. There is divergence. How do you relate North America and Europe? You ask me. I don't know. I still don't know how to answer this better. Please respond to this question I asked, response I gave you. Boundary between Pacific plate and Eurasian plate experience divergence or convergence. I've done a second question. Mr. Mahendran, please answer. Is this clear? The diagram, at least the one which I've drawn right now? Yeah, because these two are separate entities. Fine then. Thank you. Thanks for the response. Okay, that's the last one. Fine. So thank you. So see you for the next class. Next class we'll finish geomorphology with earthquakes, of course. Earthquakes will be much relatively simple. So after that we enter oceans. Take care. See you next weekend. Next weekend, yes, I've asked for class. So bye. Take care.